This is a loop. You see it? So we want to calculate an expression for the magnetic field due to a current going in a loop like this. That's what we're going to do. Okay, so I have this little loop. We need to know that first, if I have a super tiny section of current, so if I break this into little pieces, then the magnetic field due to that little piece, I can write it down like this. Okay. So this is a constant, mu naught over 4 pi. That's just your magnetic field constant. And then I have the current. dl is the vector and the length of that little piece, right? Because as I move around the loop, then the direction of the current changes. And we describe that by the direction of the piece. But the magnitude of the current stays the same. R hat is a vector, unit vector, from the location of the current piece to where I want to find the magnetic field. I'm going to find this magnetic field. Let me get another prop. So here's the axis of the ring, this pin. I want to find the magnetic field only on this axis. Okay, so I'm going to have a different piece on this axis and find the magnetic field to that piece, and then I'm going to add up all the pieces all around it. Okay, but that r hat is from the piece to the location where I want to find the magnetic field, and r squared is the distance from that piece squared. Okay, so I think we're done with the props. So let's draw this from the side. Let's say this has a radius r and a current I going through it. So this is the current comes out of the board. It's like this. Here's my ring. So I have it like this. Okay, so the current's going like this. So up here, the current is coming out of the board. Right there, the current's going into the board. And so this would be I dl right there, coming out. And I want to find, let's say this is the distance z. I want to find the magnetic field right there. Okay, so the first thing we need to do is let's draw this vector r. And that's the direction of r hat also. So if I have I dl going this way and I have r hat going that way, what's the direction of b due to that tiny little piece? Not due to the whole thing, just that tiny little piece. Well, the magnetic field, if I have the cross product dl, I dl cross r hat, then I use the right-hand rule. Right-hand rule. You've seen this. Or you could say there are two vectors that are perpendicular to both I dl and r hat. And they are a vector going this way and a vector going that way. And I use the right-hand rule. See, notice I put down my marker. I'm right-handed. So I put down my marker. So I can use my right-hand rule. And on my right hand, I let my fingers of my right hand curl through I dl and then r hat. So if I do this way, then they're going to curl through I dl and then r hat. Or maybe I could do it this way, right? And so that my thumb points in the direction. So that's the direction of db, because it's just due to that little piece. Now, let's just do it the other way. If I did it this way, I would cross r hat and then I. So that's not right. I want I dl cross r hat. So it'd be this way. D. I can write that. This video is going to take long. dB. Okay. Now, imagine as I go around the circle, I'm going to add up all those pieces. Down at this other bottom, I'm going to have another piece, and it's going to have r hat is that way, but I dl is into the board. So this is actually going to give a magnetic field like this for that piece. And so every piece in that circle is going to have another piece that's going to cancel in the xy direction and only have a z component. The only thing that survives is the z component. That's important because that's going to make it easier for us to integrate. All I care about is this z component right that way. Okay. And I'm going to only find the z component because everything else cancels. So now I don't have to deal with the vector problem. I can deal with the one-dimensional problem. So I want to write down an expression for dBz. dBz is mu naught over 4 pi. Okay, now here also I can use the other definition of cross product. If I have A cross B, that the magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of the angle between them. So in this case, that angle is always going to be 90 degrees. So sine of 90 is 1. Okay? Because look, R is that way. R and IDL are always perpendicular. So that's good. Okay? So now I'm not going to use that. I'm just going to say this is going to be I dl. R, the magnitude of R hat's what? You know it. Say it. 1. Right? Because that's where we define that. So that's gone. So then I have just over R squared. But now I have to include this Z component. So let's say if this is the angle theta now, okay, which this is not theta anymore. And that, I want the Z component of this, let's see. So this is theta, right? Because those are perpendicular. Yeah, I'm pretty sure that's theta. Okay, so the Z component's going to be right here, and that's sine of theta. So I need to multiply this by sine of theta. That's not the cross product sine of theta. I erased that. Okay, but I wanted to use theta, so that's why I erased it. Okay. Now, could I integrate all around that whole loop and be done? Well, I could, but I need to get things in terms, I need to get rid of R and theta in terms of the things I want, which are big R and Z. Okay, so right here I can get this triangle. I know R squared is going to be this. R squared is big R squared plus Z squared, because it's a right triangle. I also know that sine theta is opposite over hypotenuse, so it's going to be R over R. So sine theta is going to be R over the square root of R squared plus Z squared. So I can put this and this in up here. So I get dBz is mu naught over 4 pi I dl. Sine theta is this, R over the square root of R squared plus Z squared. And then R squared is going to be R squared plus Z squared. So as I go around this loop, this doesn't change, it's a constant. This doesn't change, it's a current. R squared, big R squared, is the radius of the circle, it doesn't change. Z is this is a parameter from the center of the thing, that doesn't change. Okay, so nothing changes except dl. But now I can integrate. If I integrate both sides, I get the integral of dBz on this side, which is bz. I get the integral of dl on that side, which is the length of the whole loop. Right? That's all. So I get bz mu naught over 4 pi. I'm going to combine these two. So I have r squared plus z squared and r squared plus z squared to the 1/2. So this is going to be I r over r squared plus z squared to the 3/2. Right? And then I have dl, integrating dl around that whole loop is the circumference. So it's going to be 2 pi r. So let's just, through the magic, rearrange things. So I have 2 pi, that's mu naught. I'm just going to put the 2 pi right there and r squared. And I'm not going to cancel these because mu naught over 4 pi is 10 to the negative 7th. And so if I cancel one of the pi's, I'd have to deal with mu naught, which I can't remember, so I just leave it like that. But it's fine. So is this answer valid? Well, a couple things. One, what happens as I get really far from the loop? The magnetic field should go to 0. So Z goes to infinity. This does go to 0. That's a check on that one. Okay. What about the units? Well, here I have mu naught IL over r distance squared. So I have the mu naught I, then I have L distance squared over, this is going to be distance cubed. Okay. So I do, this is distance over 1 over distance, so I do get that. I get the right units, so that's good too. As Z gets much larger than R, then this is mostly just z cubed. Okay, this is important, and I have a 2 there. That's important. So this is a suggestion that the magnetic field due to a loop, once you get far away, looks like the electric field due to, name it, you know it, a dipole, right? A dipole. So this is, we actually call this a magnetic dipole sometimes. And notice that it depends on the current and pi r squared, the area of the loop. Okay. That's pretty cool. Right. Okay, but that's the magnetic field along the axis of that loop. If you get off that loop, you can't do anything. Okay. The end.